This is a bit of a different topic. Well, scientifically, it's a familiar topic to many of us in this team, but it's a bit of a different tact on it in that it's not federally funded research we'll be discussing today, but rather some studies that are ongoing or about to get going that are funded by private foundations. And they're led by two glaciologists who should be familiar to many of us, Leigh and Ginny, both full professors at their respective universities, who've been engaged in glaciological research of one kind or another for 2 decades or more, and have studied both Greenland and Antarctica in various forms. So, and I'll just say, in addition to that, it's certainly true for myself, and I'm sure for many others too. They've been very supportive to earlier career scientists for many years as well in various forms, and I really want to thank them for that. And I'm sure that's very appreciated by many people. So without further ado, I'll allow them to get into the science they're up to and how we might connect to it in the future. And I think first up is going to be Leigh. And Leigh is a professor at the University of Kansas in their geology department, and I'm going to turn it over to her. So thanks again, everyone.
Thanks so much for the introduction. The 2 decades comment was maybe not, that doesn't sit so well, but yes, we've been doing this for a long time, and it's great to talk about the work that we're doing, funded from the Heising Simons Foundation at Helheim. And really this kind of came about in a couple different ways as a community. I'm assuming you guys can see my screen. Okay, if not, please put something in the chat. Okay. We've been talking about ice-ocean interactions since like 2010. And really in particular, like this boundary right here, which is very unobservable and hard to know what's happening yet. We've kind of identified it as being a critical boundary for stability of tidewater glaciers. And Ginny's talking about sediment flux there, which is also something that we have been really struggling with trying to quantify. And through like a lot of workshops, community engagement, we try to like coalesce our priorities, and a lot of you on this Zoom have helped lead or been participants in these workshops, trying to like come up with the priorities of what we need to understand, how we might set up an observing system, how we're going to quantify freshwater fluxes. And in 2013, as part of this Massachusetts workshop, and these workshops have been funded by a number of different agencies, including IARPC, I think, supported one, ARCIS, NSF has been supportive, CLIVAR, CLIC, and so we've really been fortunate to have the support of a lot of different organizations. But we identified pretty early on that these were some of the top priorities. We needed long-term observations at a number of sites around Greenland to really understand ice-ocean atmosphere processes, that we needed process studies to identify some of these systems in isolation. And also we needed a mega site experiment to understand the linkages between these processes. And this kind of strategy, while fundable and supportable in Antarctica, we can think of the West Antarctic ice streams or Thwaites, having a site with a lot of experiments taking place and observations at one place, has been really hard to support in Greenland because of our funding structure and kind of linking these, just to one spot. We're just not organized that way right now. And we're really fortunate that Heising Simons has seen that as a way that they can help out, and they got involved. They don't have proposals. They see things that they think will resonate with their CEOs and their board in terms of scientific interest, and they kind of ask for engagement. So that part is very different than our traditional funding structure. You don't pitch to them. They go to AGU, they go to other meetings and get excited about certain things and ask for more information. And that's what happened. They saw a talk at 2013 that Dave Finnegan at Krell gave about some of the observations we were getting at Helheim from Lidar, kind of patching together startup money and other funds that we could to test the Lidar there, and wanted to support it. And that's largely Gordon Hamilton's project that initiated that connection with Dave, and I was kind of tangentially involved. In 2014, I believe they actually took the science lead at Heising Simons to Helheim, and they got really excited just about the huge scale of the questions we're trying to answer and how interdisciplinary it is, and how like we were kind of, piecing resources together to get the observations that we needed, and saw a need for a kind of a bigger project than they were funding at the time. So they basically said, 7-ish PIs that were supportable, and these were the things that had been identified that were kind of rose to the top of observations and systems that we needed to understand at Helheim. And so that includes some input data of the geometry underneath the melange, which is this proglacial mixture of icebergs and like bergy bits and sea ice. And the bed topography, we need that as a better input to understand these systems. We need to understand what the atmosphere is doing, both kind of present day and some of the historic mass balance. We need to know what the ocean's doing. That's been particularly difficult at Helheim because of its melange. And so we have 2 different strategies to try to understand the fjord variability right at the melange, and then also from moorings kind of further afield. And then modeling and integrating that into a way to try to get the thermal forcing that is a function we need to incorporate into our models. And then in terms of glacier variability, the part that I've been working on are kind of high resolution velocity and calving variability, and then some different scales of models that I'll mention. And Doug, I put him in glacier variability, but he's really kind of fusing all this data together and trying to kind of minimize some of the uncertainties. So I just wanted to show one slide from each of these key projects so you have an idea and know who to contact if you want more information or to kind of get involved in some way. The geometries from that we're going to get at the bed topography. You can see from these are the OIB flight lines. Green means it has good data. Yellow is meh, and red is no data. And so near the terminus, we're really pretty scarce with good data, and particularly on the margins. And so Carl Lucien at Croesus, they're going to bring a vertical takeoff and landing platform. That the advantage of these, as opposed to the OIB strategy, is that they can fly more slowly and at lower elevations and get kind of a better signal to noise ratio over the terminus. They're also using a different radar that's less susceptible to attenuation. And so our hope is to really get a dense grid of bed topography in this critical area, which we feel like we need. For the bathymetry, this is from Luan's paper, but you can see like under the melange, which is about 20 kilometers, we are missing a really good idea of what the topography is like, or the bathymetry is like. We have some CTD casts from David Holland and Fiam, but there's a pretty big gap, and that's the important area that we want to know, that's right next to the glacier. And so he, not this year, but next year, will add measurements using either gravimetry or this multi-beam that's been tested at Peterman to fill in this gap there and then integrate it with bed machine. So those are the kind of the inputs, or the properties that we feel like are really important to do a better job of understanding these processes. The other inputs are some sense of the dynamics of the circulation underneath the melange. It's been very hard to capture in a systematic way. And so Luca Centurioni at Scripps has a sling loadable drifter that gets dropped either into an open lead or just onto the melange, and then when it hits water, it can deploy. And the idea is to do this several times, maybe not monthly, but throughout the year to get some observations year round. And then it has a long string of temperature and pressure nodes so that we can have a sense of how that stratigraphy is happening at different places along the melange, different seasons. And then Fiam has, through a patchwork of different funding agent, like 3-year grants, has pieced together like 11 years of mooring data in Sermoluk. So where the stars are here are where she has moorings, and it's very valuable to have this long record of ocean variability. And so she now has 4 years to kind of add to that variability, and from that we can pull out the seasonal and decadal fjord variability in Sermoluk. And you can see, if you only had 3 years, you're really maybe not getting this complete picture. We need to have these long term, and this is giving her the opportunity to do that, and from that we can investigate the drivers of that variability. And then finally, for the ocean piece, Ken Hughes at Oregon State and Emily Schroyer, who's now at Office of Naval Research, are taking kind of NCEP atmospheric reanalysis data, downscaling it, and downscaling MIT GCM within this model domain of Sermoluk and Helheim, so that they can get multi-year simulations of Sermoluk Fjord with the right forcings and at the right, hopefully, scale that we need for these boundary conditions. And so this is just a kind of a snapshot of some of those surface temperatures and how they're capturing that distribution at a much higher resolution than was previously we were able to do. And then Ken has a really cool approach looking at how, like within the melange, how heat can get transported through it with icebergs of different sizes. So all of these gray boxes are just kind of simulated icebergs. And one question we have is, like, if we have this warm layer, how does the distribution of icebergs impact that? Does it block it in certain ways? If they're oriented a certain way, does it matter? Does it not really matter? And some of my work will be to also give him kind of more realistic observations of iceberg sizes within the melange for that model. Stepping to the atmosphere sides, we need to obviously have all of these pieces. Marco at Lamont is downscaling MAR to 100 meters in the Helheim domain, which really kind of highlights these components a lot better in a more useful way for the kind of modeling and observations that we have, and interested in closing the water budget from what they see at the surface to the bottom of the ice sheet. They're trying to kind of validate or assess that that melt with prom ice from GAUS, their MAR, and also SAR and passive microwave satellite observations to have some limit on the extent and timing of melt within this catchment basin, so you can put better constraints on that. And then Sarah Doss is collecting some fern cores higher up in the catchment to really give us a better picture of how the variability that we're seeing now has looked in the past, decades to centuries. So she has some fern cores from early 2000s that she's extending, and then also adding a few within the catchment. And those will allow us to identify the mean state trends and extreme years of accumulation and melt, identify horizons for the radars, and kind of connect the history of what's happening upflow to what we're observing downflow, so that it's not, that we can see that kind of longitudinal impact there. And she's deploying it. She and Melissa are deploying in a month, hopefully. So we have, I'll say for kind of all of these projects, we were funded in 2019 and did some pilot tests in 2019, and then have not been able to go to Greenland the past 2 years. And so we're behind in the actually acquiring and be able to use the data in that way. And then finally on the glacier side, that's the piece that Dave and I see Adam have been working on. Gordon and Dave were originally funded to put this Lidar on the south side of Helheim. This project, kind of with this larger team, is we got the resources to put out another one on the north side. That just having one, it really only maps about halfway. And so using them together, we can get a picture of what the whole terminus is doing. And these Lidars scan every 6 hours year round, except in the winter when they're running just on methanol fuel cells, and they scan once a day. But they give a very rich point cloud data from which we can extract horizontal and vertical displacement. So we can look at questions of height of a buoyancy or flexure, or strain rates and tides, and kind of the precursors and the effects of calving within this kind of domain. For the modeling, Matthew has downscaled, or has a nested grid, I guess, of Helheim at 100 meters to 1.5 kilometers. And the goal is really to model the impacts that ocean and atmosphere variability have on the glacier. So connecting the downscaled MAR from Marco and the ocean thermal forcing from Emily and Ken into this higher resolution model. They're really showing already that they can do a really good job of reproducing the terminus of Helheim and that variability since 2007, and hoping to use the information that we're getting from these potential forcings to help drive a new calving law. And then finally, Doug is kind of connecting all of the data and model uncertainties that we have in a kind of data fusion approach, which is kind of unique in that, we often look at one model parameter and try to find look at the observations that just link to that, but all of these are kind of interconnected. And so he's trying to constrain the model parameters kind of in concert with each other and with the uncertainties that we have in the observations to reduce the kind of the amount of tuning that we do to kind of figure out the probability of these different parameters and how they're kind of related to each other. And so these are the observations that he'll be using and kind of incorporating into these model parameters. So those are the umbrella projects, and the way Heising Simons works, we are each funded independently, but working collaboratively on logistics and on the questions that we're trying to answer. They've also funded other projects at Helheim. This all-star cast of early career researchers, Winnie, Colin, and Kristen, are looking at the Fern Aquifer at Helheim. And so that's kind of in between where Sarah's Fern cores are and the terminus stuff that a lot of the observations are focused on, but how dynamic that aquifer is, how it might impact flow kind of downstream of it. And so they will be deploying kind of with our group this summer at this site and bringing a lot of ground-based instrumentation. Sridhar is actually funded before this project was to look at fracture dynamics using his geopebbles that look kind of like this, and putting out a network and trying to understand the kind of cascading impacts of fractures and how they propagate. And then Alex Robel has a larger project that looks at kind of the variability of different parameters that go into the models and how that changes the mass flux that you're looking at. And so this is looking at, just a bunch of simulations of melt and how it might impact the volume change over time. And so different, but that we're hoping our observations help inform these projects and that we're working together. Emily Arnold, who's a colleague of mine at KU in the aerospace engineering, is also bringing a different type of quadcopter to Helheim this summer as part of her career grants. So we kind of leveraged some of the logistics of this larger project to help her as a single PI do that, and hoping that the fact that we're going for the next few years opens up other opportunities to do that. We're doing a piece of what we think a mega site should be, and hopefully there are other ways we can help bring in other observations that are probably equally important as what we're already doing. Just, I know I'm probably going too long, but I wanted to just give a little bit of background about Heising Simons. They award about $135 million a year across a range of things that their CEOs and their board care about. So that's, largely education, but also science. The science is kind of focused on astronomy and fundamental physics. They also put a lot of money into women in physics departments or women in physics, climate and clean energy, human rights, and community and opportunity. And in kind of this interface of like science and education, they teamed us up with this artist in New York, Amanda, who has this project where she's doing these huge murals all around the nation and kind of with boys and girls clubs and local communities. And it's also kind of virtual reality, like you kind of scan it and you learn about Greenland and how it has impacts on their local community, like the fact that climate is changing. And so they're kind of like helping bridge these artistic and education components, which has been a nice addition for us. So that's basically an overview. We've been funded for a little while, but early in the data collection. And, we want to make this as collaborative as we can. Like many things, it funds a lot of observations and not a lot of, a few students, but not as many as the data that we'll get. And so we'll have a lot of data and you all are super clever people. If you want to work with some of this data, we would love to have your insight. And so, I don't know if we do the discussion now or later, but things to think about is like, what are we really missing, within the purview of what is possible at Helheim? And, like this is kind of a unique opportunity that hopefully will, lead to other things, foundation or more federal agency driven. But right now, it's hard to imagine how this kind of project could be funded in the Arctic. And so if there are ways that we can kind of help push that forward, I think that would be really valuable for future projects. That is all I have.
Wow, thank you, Leigh. That was excellent. You really connected a lot of dots there for everyone. I really appreciate that. I think so. Normally we try to move some of the questions toward the end, but your discussion prompts are really kind of very well suited to let's just have a couple minutes discussion on those. See if there are any folks who want to chime in on those prompts. And could you share that slide again? That was really appreciated.
Yes. Yep. That's right. Nope. This one here.
And I can certainly ask a question sort of modeled on this, but let's see if I'll open the floor first. Anyone? Just chime in because I'm not sure I can see hands. All right, well then I'll take the floor. So, I mean, as far as I can tell, you were really checking all the boxes in terms of key disciplines and sort of major unknowns that are occurring at that terminus. And in terms of the logistics of working at or near Helheim, I've flown over it, but never been there myself. And how close do you think you are to the limit of what would be possible if Helheim were indeed a full mega site? Is there, are you think that you're, another way to put it, do you think what you're getting done there is sort of 50% of what could be possible logistically in any given season, or are you approaching the very limit?
Okay, so you're asking logistically, not scientifically. I mean, it's hard to know. Like, that's one of the goals of the mega sites is to figure out what are the important things that we need to deploy at a whole bunch of other sites. Like maybe we don't need the Lidar, but we need the Fern cores or whatever to really understand the story better. And so that's one of the hopes. I mean, it's hard to know logistically because, shipping costs are like skyrocketing and logistics. Yeah. Nobody's been to Greenland tourist wise for 2 years and now everybody wants to go. So yeah, no, it's been much harder this year to plan logistically than it has been other years. I don't know if that is just a reflection of the pandemic rather than the fact that we have more people there. I mean, there's plenty of, it's, helicopter limited and probably lodging in Cyclic, where we jump off limited at this one spot, but there are other spots, the other glaciers that are also super important that could, house a different type of logistical purview. I mean, this is Helheim is important because we feel it's very important because it is very variable. We have some long-term records already, and so we wanted to leverage that, but it's also a really hard glacier because it is, has this melange, which makes everything impossible, but also really interesting. Like, we don't understand a lot about the melange, and so there are kind of two approaches. Either we go to one that doesn't have this complication, but Helheim and Jakobshavn and Kängör, do have, they're contributing a lot of the mass loss, and they do have these pretty permanent melanges. And so I think our strategy was to try to do what we can to understand them, but that is definitely adding to the logistics burden.
Kind of following on that,
yeah.
It seems like maybe the other need that megasite requires might be because these glaciers are so time varying that having observations full year, it sounds like you do have some observations that are going all year, and like maybe having any of those inform us about how much we need to get in the off season, because we're all going there, in this one time period where everything's going like gangbusters. And so we don't really have a sense of how much these processes are occurring in the wintertime.
Yeah, I mean, I feel like we've already learned a lot about calving in the winter from the Lidar. I mean, scanning once a day, but that's plenty for what we're doing, and hopefully we will get some melange, variability estimates from Luca's work. But it's, as you know, it's super hard to get these observations in the winter, and we really need also better local local contacts, or and I do think that that's something that, hopefully our agencies can help with it. It is not helpful to have a local contact for a 3-year grant. We need a permanent person in the towns that we are really focused on to have a long-term commitment to like the local science relationship. It does not happen in 3 years. In fact, it does a lot of negative impact for us all to show up with all our fancy instruments and try to get people excited for a year.
Yeah, great points. Yeah, thank you very much, Leigh. And also, by the way, thank you for your slide on connecting to other Heising Simons Foundation projects and Emily's career, because that sort of helped make the linkages certainly a little clearer for me, for someone who was removed. So I'm sure it helped others too. And you mentioned the third of the big three there, Kängör, which is a harder push than Jakobshavn and Helheim. So I thought you made a good point that, what we, and Ginny too, like learning what's going on year round at this site is going to be very important for what's going to be a harder place if we feel we'll be there later on in Kangerlussuaq. Well, thanks. Well, thank you again, Leigh. And I think now we'll move on to Ginny.
I have a question, or should I wait with it, or?
No, go ahead, Osa.
Hello, I wasn't sure if I can wait if you don't think there's.
No, it's fine. I just can't see the hands very
well.
well.
I see. Okay. All right. Well, thank you. Thank you so much for this presentation. And I gotta apologize. I was slightly distracted by some things during your talk, but yeah, definitely super. So maybe you said this, but one thing I thought about when you mentioned the many observation was didn't cover, how about remote sensing, like satellite remote sensing and stuff like that? Is that something? I noticed you had UAVs, which sounds super interesting actually, that particular sampling. But that was like one thing that I thought that but maybe I missed it, where maybe there.
No, that's a really good point. I didn't mention it explicitly. Through some other projects, a number of us have those pieces, and so we are sharing the velocities, the terminus positions, some of the other data. We did not ask Heising Simons for support for that, because we really wanted the money for the instrumentation and the targeted modeling. But that's, you know, like every project, that's the stuff that you do like on the side, or that you try to find money for a student to pull together that's separate from the project. But absolutely, like there's a lot of remote sensing data that can and will be used.
And maybe that's also an opportunity for other people here who might be interested.
Absolutely. Yeah, I mean, we'll have some like ground truth data to help, or to fill in some gaps, or to work together with. So yeah, really good point.
I have like
I want to cut into Ginny's time. I feel like I've.
Oh, should I stop? I'll wait then. I have. Go ahead.
Thank you. Great question. Leigh, Peter had a question for you in the chat, but I think we'll let Ginny start her presentation. All right, take it away, Ginny. The scaling is a little bit off. Is everyone else seeing the scale? Okay, you've got it.
Okay. Hi, everybody. Thanks for the opportunity. Unlike Leigh, we just found out about our funding in December. So this is really just our proposal to Keck that I'm going to talk about. And but we have sort of similar requests that, you know, the foundations provide a big injection of funding, but most of that funding is really just going towards getting these observations. There's only one student on the proposal that's getting salary, and the rest of us are going for free. And so we do need to write additional grants to do analysis. And if anybody out there wants to do analysis on some of the data we're collecting, we're open for collaboration. And so this project, we tried several years to get funding through NSF, but they would not bite, in part, I think, because it's a fairly risky proposal, and because it was very expensive. And the idea really relies on this vehicle called the Nereid Under Ice vehicle, which is a AUV/ROV that is operated out of Woods Hole Oceanographic Institute, that's used specifically for near ice exploring, and I'll get into that in a moment. You know, our motivation is the motivation that a lot of us have, which is really trying to understand future sea level. And this is showing past sea levels, and that added meltwater, which is ice sheet and glacier melt, is really one of the largest contributors to sea level. And so we want to be able to predict it into the future. But that's become quite problematic, in part because there is a range of human behavior that affects, you know, the amount of forcing we're pushing towards these glaciers. And so even if we pick a future that's based on sustainability, we're looking at sea level rise of about 0.5 meter. And this is from the last IPCC report that came out. The cool thing that this report included was this dashed line, which I consider a win for glaciology, because it really interjects this, it interjects this like amount of uncertainty that we have with the marine ice sheet instability. So it's called this low likelihood, high impact storyline related to the marine ice sheet instability processes. And so many of you know the marine ice sheet instability is retreating terminus on top of a retrograde bed slope that leads to a runaway effect that allows for more mass to be lost. And so this is sort of related to the process that we're interested in studying for this Keck proposal. The Greenland ice sheet experience is sort of a mini version of the marine ice sheet instability within each of these glacier fjords. I'll show this movie, which is a little movie of how the terminus retreats for this one glacier. This is Umyamako Isbrae. The glacier is located here and the ocean is here. This is the terminus boundary, and the blue just represents the mass conserving bed, and then the ocean bathymetry on the seafloor. And then this is a transect along the center line of the fjord, with black being a prograde bed slope and red being a retrograde bed slope. And this glacier was perturbed by the climate in around the late 1990s, when most of Greenland's glaciers experienced widespread retreat, acceleration, and thinning. And so around that time, you see that as soon as this glacier gets to the retrograde bed slope, it begins to retreat in a runaway effect until it gets to an area of prograde bed slope where it can restabilize. And so the idea here is that the climate merely serves to push the glaciers into a new dynamic state, but it's the topography that regulates how much change can happen. And that concept may help to explain why we see this variability in glacier dynamic response to climate perturbation over the satellite era. So these are two really interesting results, one from Tavy Murray on the left and one from Beasatho on the right, showing terminus change from 2000 to 2010, and then elevation change of outlet glaciers over roughly the same time period. And we see that a lot of glaciers are retreating. There's red circles here. The circle size indicates how much retreat's happening, but there are some glaciers advancing, and there's quite a bit of variability in how much retreat is happening. And there's a lot of different symbols in this plot here indicating the elevation change behavior of outlet glaciers. In general, we see a lot of pink dots, which indicates glaciers are thinning in response to this climate perturbation. But there's a lot of heterogeneity in the behavior of the elevation response as well. And so this indicates that there's maybe something more going on than simply the climate really causing a lot of these glaciers to change. The amount of change might be related to the geometry of the system. And so this was another result that came out by Doug Brinkerhoff. He had this really fun little model that shows a glacier in cross section. The surface is here. This is sea level. The black line represents bedrock, and the red line represents the sediment that's being created through erosion. So it's a coupled ice and sediment model, and it allows for glacier variability completely outside of any climate forcing. And so this shows the seesaw pattern up below, shows the terminus over time, terminus position, and you can see this, this slow advance, fast retreat behavior that occurs simply because of coupling the ice dynamics to sediment dynamics. And so this suggests that, you know, if the glaciers are so sensitive to topography, that if topography can be built and destroyed so easily through sedimentation, that sedimentation may also play a role in controlling or impacting glacier dynamics to some degree. And so the other motivation was that a recent paper from 2019 suggested that Uplift can create new topography. So as glaciers retreat, they unload the bed, and that unloading allows for a rebound of the surface lithosphere. And that uplift can also create pinning points, which can stabilize or slow retreat of glaciers. And this paper came out suggesting that uplift rates on the order of about 10 centimeters a year might be important to consider in terms of slowing or stabilizing glacier retreat. And there was also a very compelling paper that came out in Nature Geoscience that suggested we could geoengineer solutions to save our glaciers through building topography, artificial topography, both berms that keep the warm ocean away and bed bumps that can help stabilize glacier termini. And so we're not in the business for this proposal of trying to come up with geoengineering solutions, but the idea suggests that, you know, topography plays this really critical role in controlling glacier termini that I think we haven't quite taken into account so much. So we had this is a colleague of mine, Sean Gulick at UT, University of Texas, and he collected some data with some other people in front of Hubbard Glacier using this bluefin AUV from 2014. And the idea was to look at how much sedimentation was building in front of Hubbard Glacier. And so they have this survey of data. This is just colored by the depth of the seafloor. And they did 2 repeats of this profile here along this gradient from purple to red, getting as close as possible to the glacier front. And that's what's shown here. So they had an earlier multi-beam profile in 2004, and then this AUV profile in 2014. You can't quite tell, but in this profile, there's quite a bit of detail because it's an AUV, so it's a much higher resolution sensor than the multi-beam. But the real thing to notice is that there's about 80 meters of accumulated sediment in just 10 years. That's 8 meters per year of topography being built at the grounding line, which is much, much higher than this rate of uplift that's been suggested to be important for ice dynamics being slowed in terms of retreat. In addition, the AUV can provide imagery of the seafloor topography at a very high resolution. And so you can see these features that are called cyclic steps. These are from this area of the seafloor on the sort of lee side of the moraine sloping away from the glacier. And the idea here is that these are diffusive bed forms. So as the sediment is moving down the slope of the moraine, these bed forms are created. And so it's basically this kind of information that we're hoping to get with the NUI. There's been a ton of studies in Greenland and elsewhere that have looked at sedimentation on the seafloor in front of glaciers, but very few of these happen, or like almost rarely do they happen at the active glacier terminus. So they're all examining paleo moraines and not really looking at the modern day moraines that are getting built. And there's good reason for that, because the terminal environment, as you saw in Leigh's talk, is a really complex and difficult environment to work at. This is a movie put together by James Bailog for Rink Glacier, which is one of the glaciers we plan to study. These glaciers are highly changeable. The environment can change in a second as you get giant tabular icebergs that calve off and melange that fills the fjord. It can be quite a dangerous place to work because of calving icebergs and tons of crevasses. And they're often pretty inaccessible because the melange creates a barrier between the ship getting close enough to the area of interest. And so our proposal is really to get into these environments and collect data of the sedimentation happening at active glacier termini. And we're picking 3 different glaciers that we have studied quite a bit in the past through funding from NASA. So these are our 3 glaciers. Rinkus-Bray was the movie I just showed you. This was the one that had the retreat that I showed earlier. And then Kangerlussuaq-Sormsua is the glacier that has been stable over the satellite era. Rink has experienced a small retreat, and Umiyamako has experienced a much larger protracted retreat that then the glacier restabilized in about 2009. And so the idea here is that by looking at a set of glaciers with a divergent retreat history, we can explore the relationship between not just the sedimentological properties we hope to observe, but the ice dynamic properties, both in situ and over the satellite era, so that we can build parameterizations that allow us to improve the models of coupled sediment and ice interactions. So this is like our hypothesis of what we think is happening in these marinal environments. We identify 4 processes that are probably contributing to the changing topography in front of glaciers. So there's thermomechanical sediment being brought to the front. This is usually sediment that is frozen into the base of the ice. Mechanical deformation just from pushing, from the ice flow, pushing into the sediment in front of it. We expect that glacial fluvial sedimentation will be the dominant mechanism for delivery, both through the plume, but also through a bed load that's delivered at the base. And then we expect mass movements or diffusion to contribute to loss of the moraine on the lee side of the slopes. And so the idea is to take a ship in as close as possible and do marine geophysics from the ship as close as possible, but then to deploy NUI via a cable I'll get into in the next slide, to the glacier terminus. And so NUI can operate in 2 modes. It can be a remotely operated vehicle, and it can transit in this kind of closed embayment mode where it can do mapping. And then it can also open up and have a retractable arm to do sampling as well. You can put a bunch of instruments in this workspace so that it can collect additional geophysical data in close proximity. If it operates via this fiber optic, so it's a very thin, it's this one, very thin fiber optic cable that can go up to 20 kilometers away. We're not sure if that will remain intact in this kind of environment, since it's the first time that NUI's been used in an ice terminal environment. But NUI can also operate as an AUV. If the fiber optic breaks, it'll follow a predetermined path back to the ship where it can be recovered. And so our field plan is kind of shown here, where we have these white lines indicating where we plan to get sub-bottom profiles from seismic surveys using the ship. And then we want to get some cores from the ship also in white. And then these pink dots indicate all the moraines that we're interested in sampling. And then NUI will get in to do these close surveys along each of the termini. We hope to get maps across the complete glacier terminus from high resolution imagery and high resolution bathymetry from NUI, and perhaps do repeats as well over the time period that we're there, so that we can look at how have bed forms and how has sedimentation evolved over that time. So just a little bit of detail about the deployment. We require a fairly big ship, which has been most of my headache lately, to operate NUI. It works via this large canister that gets deployed with it that has the spooling fiber optic. So both of those will go overboard. The spool stays in place and NUI will transit with the remote operation to the place that we're interested. It'll do some real-time mapping, and we can be seeing this as we're mapping it from the ship. We can also operate the arm and do sampling from this remote distance. And then it can do a semi-automatic transit back where it can acquire maps as it's coming back to the ship. And then it gets recovered, brought back to the ship, and redeployed the next day. So it's not just about NUI. There's a lot of additional observations that we're kind of trying to put into this, including remote sensing, some bed topography and surface mass balance data to kind of feed, all of this will try to feed us the ice dynamic properties that we're hoping to link to the sedimentation that we're going to observe. From NUI, we want to do this detailed mapping of the bed forms at the terminus space and getting samples so that we can look at the grain size and do grain size analysis. And then we also plan to put out sediment traps using NUI. We're going to put out some ocean bottom seismometers that also have acoustic sensors within the housing, and those will all be deployed for a few days because we think for each fjord we can potentially get almost a week's worth of data to look at rates of runoff and possibly bed load from an OBS. And then from the ship, we're going to be doing this seismic sub-bottom profiling, like I mentioned, multi-beam and coring. And so this is the team that we have. I wrote the proposal with these four, but it really is based on work that was, long time in the making, including Doug Brinkerhoff and Becca Jackson. And then we also brought in Ben Kiesling, who's going to be at UT starting in a couple months, and Julian Dowdswell, because he's worked in the area extensively to act as people to help, with interpretation of these data. And so this is the other person that we've started to talk to as well is Emily Edom, because she works a lot on suspended sediment from glaciers. And so we're going to try to write an NSF proposal to get the analysis part funded. And then my last slide is just a little bit about the Keck process. Many of you who are at big R1 schools will probably hear a call for internal solicitations to submit for a Keck. The Keck only allows 2 proposals to come out of each institution per round. They have 2 rounds per year, and 1 proposal represents a medical field and 1 proposal represents a science field. And so we won the internal competition within the University of Texas, and we submitted a 3-page concept proposal to the Keck Foundation. And this all happened within 1 year. So we got the internal yes, I think in January, February. We submitted this phase 1 application in like March. And that has no budget. It's pretty straightforward to put together because it's just 3 pages. It's just hard to get it into 3 pages. And then if you're selected, the down select is, I think, 30% to go from phase 1 to phase 2. Then you submit a 12-page proposal with a more detailed budget. And that proposal includes a site visit, which during COVID was remote. But we did a presentation to the Keck team, including a Q&A about the proposal and how we plan to pull it off. They make funding decisions. The down select from phase 2 to actual funding is about 50%. So if you get to phase 2, you have a much higher chance of winning. And those funding decisions were made in December. Though the proposals, these 12-page proposals, are reviewed externally, and the people they have internally are also like really smart people. They asked a lot of really smart questions. The typical amounts are around $1 million. We put in a request for additional funds, which was granted because we had such high logistical costs, including renting this boat. That still remains to be seen. And then Keck doesn't pay significant salary support, and they don't pay institutional overhead. So we got a 1.5 million, and that is just a blank check. Well, not a blank check. It was a check of 1.5 million for our project, for us. So it was a really great win, but it feels like it's kind of halfway there because it really doesn't provide any of the funding to do the analysis and to hire students to, do the bulk of the analysis for us. We also had a lot of support from our internal vice provost for research office that really has worked with the Keck Foundation quite a bit in order to make sure that we were meeting the needs of Keck, which are like each foundation, I think, is probably pretty unique and sort of like what they're looking to fund. And so we had a lot of support from them to get to the sort of other side of this. And that's all I have.
Awesome. Thank you, Ginny. Really well motivated and really exciting stuff. I can't wait to see what NUI does. Good luck finding a boat.
I know.
And thank you for the review of the Keck process too, because it seems a little closer to what we're familiar with, although there are obviously some differences, but they're certainly quite different from Heising Simons as well. I'll open the floor to questions from the audience. I cannot see hands, so just chime in and fire away. Oh, Leigh, go ahead.
I just put this in the chat, but there's so many advantages of the foundation. I put some of them, I listed some, but I don't think they're going to be the savior of like some of these projects, and nor do we want them to be. The review process is different. Heising Simons and Keck have paid a lot of attention into the logistics or the like infrastructure of how they do things, but not everyone will. And that might be really detrimental to how we share data. They don't have the same requirements that our federal agencies do. They don't have the same like rules of, protocols of going to the field that NSF or NASA does. They don't help with logistics, like Ginny has to find her own boat. We have to find our own helicopter. I mean, this is all, we're very fortunate to have this money, but it's not the same. And I don't want it to be seen as like, well, as long they'll like figure it all out. There are downsides of like, trying to get a whole bunch of foundation money for our community that I think is just worth knowing about or thinking about a little bit.
Absolutely. Ginny, do you want to add anything there?
Yeah, I would just say that like Keck really focuses on high risk, high reward. And so, that's not something that I feel like NSF is comfortable with. And so I think that they fill a niche, but there's a need for coordination that is missing, I think, when you have foundations kind of coming in and it's not as well coordinated. And so that's where it's sort of dependent upon the PIs to be more coordinated with the existing funding agencies. So we're trying to work that with the with NSF's ANS program.
Yeah, that makes sense. Yeah, you mentioned that during your talk too, that you had tried previously with NSF, but you considered too high risk, high cost. Do you think that that's a function more of where we find ourselves in our discipline versus other disciplines? Like I could think of, particle physics that does involve quite a lot of risk and certainly huge cost, but they still exist. So maybe we just need to shift our mindset to a degree.
I think that the cost of doing some of the kinds of things that we've identified that I think our community, like, I don't know about the sediment thing, that's sort of a new idea, but Leigh's work is community identified, as she had put out in that one slide, 3 different workshops, the community identified, this needs to happen. It's really expensive science, really expensive. And what is the NSF budget for polar programs? Like, it's not much, and it's split across multiple programs. There's no home for glaciology within the NSF that is outside of the polar programs. There's no coordination, very little coordination. I'm sorry, I'm going to like bad talk all the funding agencies, but there's very little coordination across multiple funding agencies to do really big science like this. And so it does, like, the funding from these foundations, I think, provides that avenue. It provides this sort of burst of activity that kind of shows like, oh, this is really important. Maybe then it will spur new funding within these other agencies. But the thing I think we need to think about is how we come up with new money, because we're not going to change how the pie is sliced at these agencies. We need to convince, like, there's this new pot of money, I think, from NSF for like applied science, right? So we need to think about, like, what is it in our field that is going to be applied science that we can carve new areas of research that would benefit glaciology. Probably put my foot in it for all the NSF and NASA people here. please feel free to put me in my place.
I know we had at least one program manager on for a little while. Torsten, do you want to say anything to that?
No, don't put him. Or just tell me I'm done.
I'm being completely put on the spot here. No, I mean, I think it's great that you're getting money, and that is fantastic. And actually a question for Leigh. So the foundation contacted you and then you put together a team, or how did it actually come about? I'm curious about it. Then I answer your question, Ginny.
That's a good question, and it was a process I was not super comfortable with, to be honest. I mean, it was very lucky to be in the position, but you know, they had already funded Fiam as well, and they wanted to know kind of what pieces and what group would work well together to fill those variables that we'd identified already. They had people in mind based on things that they had seen. And so it's kind of like collaborative in figuring out who might have the instrumentation and the expertise to be able to do that. And yeah, I mean, that part, I mean, it's both nice because I know we work well together, and that's a really important piece of collaborative work, especially when you're really funded for the instrumentation and not the collaboration. But it's a little bit not how we want to do science. It's a little bit like pick your friends, and we tried not to do that, but that was kind of their ask of picking people who will answer the question that you will work well with.
I mean, you know, in general, it's fine for a PI to put together his or her own team, right? That's perfectly fine. That's your prerogative. If you're putting together a team, that's up to you. Yeah, coordination between NSF and NASA. I mean, we're trying to do better, right? I'm talking with Cutler a lot. I'm talking with NSF a lot. We're trying to have these, joint workshops more and more to actually do exactly what you're talking about, to coordinate field work better, to coordinate efforts better. In the biggest of pictures, it's complicated because it is on Congress who says, hey, you guys get so much money, you guys get so much money, and and it can be quite complicated in detail, but it's something that I'm trying, together with the people at NSF, we're trying to do better at our level to coordinate efforts better, and maybe we can come up with something that is bigger. And that's something, I've been talking about with Cutler. Can we pull something, put something together? Because, you're 100% right. These things are, very expensive. And how do we fund these, these bigger efforts that, need to be funded? Because, if you commit big money, you get, big results. I mean, that's simply as it is, right?
Well,
as simply as it is.
Brings up a good point here that, our community has grown significantly, in part because the research has become that much more pertinent, and yet the funding remains pretty flat over time. And it's like the agencies aren't agile enough to adapt to what is needed from science. So there's still I read these articles about billions of dollars going into CERN, and I'm like, why do we need to know about that? Why do we have missions to Mars? But, that's just my personal beef, but how do we get increases in funding?
Yeah, it's an interesting one, and it's tricky, right? And I tell everyone who wants to know, for NASA, get involved with missions, because, missions have just, generally bigger pots of money than we have, than we, just pure R&A has. And R&A is so small, our research and analysis funds, compared to missions, compared to other, these bigger efforts. And yeah, it's a tricky situation. And yeah, if you complain to my bosses, that may help me, honestly, if that makes sense.
Yeah.
Yeah.
But if there's stuff that the community can do, I think it would be helpful to know.
Yeah. Yeah. I have to run to a different meeting, but it's a really good discussion, and we can pick this up at one point. I really would love to pick this up at one point, to talk with, with the community about how can we do these things. Similarly, I want to follow up with you guys at one point about, you mentioned, you get paid for doing the experiments, but not for doing the science with it, right? And this is a discussion we also should have.
I'm also happy to share my proposal and share the budget with people if anyone wants to see it. It's pretty bare.
So that's another discussion I would like to have at one point. How if you take all these measurements, it would be foolish, for NASA or for NSF, probably more NSF because more NSF like work, not to get most of the science out of it that is possible, because relative to the effort that it takes to take the data, funding some science is not as much money necessarily.
So we are submitting a proposal for June as our target to do the analysis and modeling with Doug and all the people that were on that slide. So I'm hoping that will get funded.
All right.
No, that's great. I really need to run.
Yeah.
Sorry, we should have this discussion, more of that discussion. I think it's good topics. Bye, everyone.
Thanks,
for being willing to be put on the spot. And
anytime.
we are past the top of the hour, so I do want to be respectful of people's time. I do want to say,
hey, Joe.
Go ahead. I am going to promote vlogs if you're.
Yeah, that's what I was going to do. So in a couple of weeks, Joe is actually on the team leading the Future of Greenland Ice Sheet Science workshop. And some of you may be familiar with the PARCA meeting and Geo Summit that used to happen in the past. NSF and NASA have kind of joined forces to plan these meetings along with the steering committee that Joe is on together. So that will be another great place to talk about some more collaboration and better coordination that can happen between federal funding agencies to better streamline field work. So I'm happy to drop the link for that in the chat. Joe, I think the registration is closed, but I imagine since it's online, it's really not that big of a deal if folks register late at this point.
It's not closed. What you hopefully have filled out previously, if you're Greenland ice sheet interested, it was an expression of interest formally. And so we are about to send out a link for you to submit, to formally register and submit a one slider that you will have an opportunity to present on the first day, April 6th. And it is not exclusively about federal funding, but it is sort of tying into some of these ideas, especially relevant to what Leigh was presenting on building up on what our community identifies as key needs. And we'll be doing that annually and revisiting that in subsequent years, hopefully not just online. And putting those forward to help rally the cause to get some of those key things done in our community. So yeah, please attend FOGS if you can. I do want to come back, Ginny, very briefly. 8 meters per year of sedimentation. Holy moly, that's
crazy.
If that's anything close to that is happening in those Greenland outlet glaciers, wow, that's going to be a big deal. So I'm very, very excited to learn more about that and how it interacts. That's really cool. So any last minute questions or questions in the chat that I may have missed? You see, Caitlin mentioned Alaska glaciers and USGS. Certainly for FOGS, it's fairly specific to just the Greenland ice sheet, but that was sort of from above determined focus. But yeah, definitely still lots to think about in those domains, and there's certainly cross-pollination of ideas still going on as well. Any last minutes? All right, well, thank you again, Leigh and Ginny, very much appreciated your time and great presentations. I learned a lot. I hope you all did too. So thank you. Be well and take care. Bye.
Thank you. Bye.